All right, let's talk about Python performance. For too long, it's felt like this dark art, right? A lot of guesswork, a lot of crossed fingers. Well, today, we're gonna change that. We're gonna turn it into a real, professional engineering discipline. We'll cover how to build for speed from the ground up, how to diagnose bottlenecks like a pro, and then how to apply some seriously powerful cures. So, yeah, let's grab our stethoscopes and get right into it.
So let me ask you a question. Think about the last big project you worked on. Is that thing a solid fortress, built to last, ready to scale and handle whatever you throw at it? Or is it more like a delicate house of cards, where you're kind of scared to touch anything because the whole thing might just topple over? That right there, that's the core question of software architecture.
And this brings us to our guiding philosophy for this whole thing. We're gonna treat our code like a doctor treats a patient. First, you build healthy habits with good architecture. That's preventative care. Then, when a problem does pop up, you diagnose it with the right tools. You don't just guess. And only then, once you know exactly what's wrong, do you prescribe a specific, effective treatment.
So let's start with that preventative medicine, building a strong foundation. This is all about the blueprint, the architecture of your system. You get this part right, and trust me, you'll save yourself from countless headaches down the line.
This right here is the whole philosophy in a nutshell. You have to remember code is just communication. You're not just barking orders at a computer. You're trying to explain your logic to the next person who has to read it. And you know who that person is likely to be in 6 months? Yeah, it's you. Clear, well-organized code is basically a gift you give to your future self.
So how do we get that clarity? We get it through modularity. This is the literal antidote to what we all call spaghetti code. You know, that tangled, horrifying mess where you can't change one tiny thing without breaking 10 others? Modularity is the opposite. It's about creating these self-contained, logical blocks that are easy to understand, easy to test, and easy to maintain.
Look, your whole system is built out of functions, and the best functions follow one simple, beautiful rule. Do one thing and do it well. Here's a super practical tip. If you find yourself describing what your function does using the word and, like, oh, it calculates the tax and it updates the database, that's a huge red flag. It means it's doing too much. Split it.
And if functions are the verbs of your system, then classes are the nouns. They're the things, the entities. And this slide just perfectly illustrates the single responsibility principle. A class should be like a chef's knife. It's specialized, it's precise, it's amazing at its one job. What you really want to avoid is creating a Swiss Army knife class, what we sometimes call a God object, that tries to do everything. It feels convenient at first, but it quickly becomes a nightmare to manage.
And finally, for our architecture section, we've got the DRY principle. Don't repeat yourself. This just means creating one single source of truth for every bit of logic in your system. We've all been tempted to copy and paste code. It's fast, but it's a trap. Because when you find a bug in that logic, you now have to go on a scavenger hunt to find every single place you pasted it. You miss one, and boom, you've got bugs and inconsistency.
Okay, so we've built a healthy system. We've followed the rules. But even with the best architecture, performance problems can sneak in. That's when we have to take off our architect hat and put on our detective hat. It's time to find exactly where the pain is coming from. And we're going to use data, not just our gut feelings.
This is the first rule of Performance Club, and you have to get this into your head. The legendary Donald Knuth said it best. The thing is, our intuition about what makes a program slow is almost always wrong. We think it's that one complicated loop, but we don't know. Trying to optimize without measuring first is not just a waste of time, it often makes the code messier and harder to read.
So what's our #1 diagnostic tool? It's Python's built-in profiler, cProfile. And the keyword here is deterministic. Unlike some tools that just take random samples here and there, cProfile watches everything. Every single function call, every return. It gives you a complete, precise accounting of exactly where your program is spending every last millisecond. So when you run the profiler, you get a table that looks something like this. Let's just focus on the important stuff. Encalls is easy. How many times did this function get called? If that number is huge, you might have a silly loop. Tote time is the total time spent inside that one function. It's perfect for finding a single, slow calculation. But honestly, the real detective work is usually in come time. That's the total time, including all the other functions it calls. A function with a low tote time but a high come time is a classic bottleneck. It's not slow itself, but it's calling something else that is. Now let's be real. Staring at a giant wall of text from the profiler isn't exactly fun or intuitive. And that's where visualizers come in and save the day. Tools like SnakeViz can take that text output and turn it into something called a flame graph. And suddenly, the slow parts of your code are just these big, wide blocks on the screen. It makes the bottlenecks literally jump out at you. It's impossible to miss.
Sometimes, though, cProfile is a little too broad. It'll tell you which function is slow, but not which line inside that function is the real problem. For that, you need to zoom in with Line Profiler. And what if your program is fast, but it's eating up all your server's memory? Well, for that, you've got Memory Profiler to hunt down those really expensive memory leaks.
All right, we've done it. We've found the bottleneck. We have hard data, we have proof. We know exactly which function is causing the problem. Now, and only now, can we move on to the treatment. It's time to bring out the big guns, the turbochargers we can use to fix the issue.
Let's start with one of my favorites, a tool that feels like magic, Numba. It's a just-in-time, or JIT, compiler. In plain English, that means for functions that are doing a lot of heavy math or running through big loops with NumPy, you can often just add one single line of code, this @JIT decorator you see here, and Numba will, on the fly, translate that Python code into super optimized machine code. The performance boost can be absolutely insane for almost zero effort.
So Numba is fantastic because it's so easy. But what if you need every last drop of performance? What if you need absolute fine-grained control? Well, that's when you reach for Cython. And as you can see, it's a clear trade-off. Cython lets you mix Python with C-style syntax, which gives you the raw, unadulterated speed of C. The trade-off is complexity. You gain ultimate power, but you lose that beautiful one-line simplicity of Numba. But what if your bottleneck isn't even about computation? What if it's just moving data around? This is where PyArrow is a total game changer, especially for big data folks. Its secret weapon is something called zero copy. So instead of System A making a copy of its data to send over to System B, PyArrow sets it up so both systems can access the exact same data in memory. There's no copying, the savings in time and RAM from this are just massive. Here's a quick tip for all the data scientists out there. You've probably done this. You have a big Pandas data frame, and you chain a bunch of operations together. Well, behind the scenes, Pandas is creating a whole new temporary data frame for each one of those steps, which wastes a ton of memory. If you use pandas.evaluate instead, the whole calculation happens in one single optimized pass. It's a simple change that can make a huge difference. So let's bring this all home. We've been on a whole journey here. We started out as an architect, building healthy systems. Then we became a detective, diagnosing problems with precision tools. And finally, we became a doctor, applying powerful, targeted cures.
If you remember nothing else from our time together today, remember this number. The entire discipline, this whole professional approach, boils down to a simple three-step workflow. Think of it as the oath every performance engineer should take.
And here it is, our entire journey on one slide. First, you architect for clarity. You build clear, maintainable code before you ever worry about speed. Second, you profile for proof. You use data and tools to find proven bottlenecks. No more guessing. And third, you optimize with precision. Only then do you apply a targeted cure to the specific problem you've identified.
And really, this is the most important thing to take away. Following this process isn't just a party trick to make your code run a tiny bit faster. This is the difference between being a hobbyist and being a professional engineer. It's about building systems that aren't just fast, but are also robust, scalable, and honestly, a pleasure to work on.
So as we wrap up, I'll just leave you with this one question. Think about the code you're working on right now. Based on everything we've just talked about, where would you start? What part of your code base is probably due for a little checkup?